Alright, this is 6.3, central limit theorem. Alright, I'm going to read this off, and then we're going to pull out the important stuff. As the sample size n increases without limit, the shape of the distribution of the sample means taken with replacement from a population with mean mu and standard deviation sigma will approach a normal distribution. This distribution will have a mean of mu and a standard deviation of sigma divided by square root of n. Alright, so what does this mean? It actually means a lot, and without it, we can't do a whole lot when it comes to statistics. But let me just give you the three highlights from this. Those are the distribution of the sample means. So we have some distribution, we don't know what it is, don't really care what it is. When we're sampling from it, alright, so the sample means, we're taking the means of the samples we're taking from it, those will themselves be normally distributed. I'll explain a little bit more on the next slide. Okay, but rest assured, they are normal, and that's important. Now, moreover, the mean of the samples, do you see why I use the notation mu sub x bar will equal the mean of your population that you started with. But the standard deviation of your sample means, so sigma sub x bar, will equal sigma of your parent distribution, the one that we were coming from, divided by the square root of n, the number of samples that you took. Alright, what does this mean? This means a lot. Very specifically, let's look at this picture. If I have some random distribution, and here I have something that's trimodal, right? It has a known mu and a known sigma. And what I'm going to do is I'm going to take a sample from this population, find the average, and plot it. All right, let's say it was a little bit bigger than the mean, so I put a little dot above the mean. All right, let's take another sample, and another sample, and another sample. And another sample, and another sample, another sample. So right now what it looks like is I have a little lump centered about the mean. If I keep taking samples, what we would discover is that we get a lump that looks normally distributed, centered at the mean of our original distribution. So if I try to plot my sample means, I will look like a normally distributed plot. My mean will be in the same place, so my mean will equal the same thing. So notice the notation I used here, sigma sub x bar is equal to the mean, but my standard deviation, you see how it's much tighter than the parent distribution? So it equals my old standard deviation, except I have to divide by the square root of n. That's what it tells us. Okay, what does this really mean, though? I will get into the next one where we actually apply it. What I want you to get out right now is, from the central limit theorem, there are three main points. Point number one, I'm taking samples from a parent distribution, I'm finding the average and plotting it. Those averages will be normally distributed. More to the point, they will be normally distributed, and their mean will equal the mean that you started with in your original distribution. Their standard deviation, though, will be related, but won't be exactly the same as the parent standard deviation. It will be the parent standard deviation divided by the square root of n. Notice the notation here of mu sub x bar and sigma sub x bar.